Hello, and welcome to our virtual session. Today, we will be talking about our joint work with Wargaming and improving gamers' experience in World of Tanks. We start with our first work on improving performance on mainstream computers and ultrabooks. We will tell how the engine was gaining support for new APIs, how World of Tanks 1.0 update redefined visual experience in the game. We will tell how we were re-architecting the engine to gain support for the modern CPU architectures, how we were adding features like concurrent rendering, simulated tank threads, how we added support for Havoc distractions and AVX2. Finally, we will talk how Wargaming want to increase shadow quality with ray tracing. We have three presenters today: myself, Philippe Gerasimov, Senior Game Application Engineer at Intel, and my colleagues from Wargaming, Denis Ikhmuhamedov, Rendering Engineer from World of Tanks team, and Branislav Sviglov, Rendering Lead from the same team. If you never heard about a World of Tanks, it's one of the top online multiplayer games. It was released in 2010 by Wargaming, and this year celebrates 10th year's anniversary. During these years, it gained support for more than 160 million gamers worldwide. It achieved 4 prestigious Golden Joystick Award and even have won Guinness World Record. It's mainly developed in Wargaming office in Minsk, Belarus, and it's a game about tanks. 15 by 15 online multiplayer battles. So 160 million gamers means enormous amount of gamer computer configurations which game need to support. And our first task when we started to work together was to support as much gamers as possible, particularly those with not very new PCs, with mainstream configurations, with new laptops called ultrabooks, which are thin and sleek, but also have small power envelope, which limit performance. And when we did our first tests, we found out that performance is about half of what we need, something like 15 frames per second. And the game misses some features like shadows. So our first task was to add shadows. Ultrabooks have Intel Integrated Graphics as GPU, and Intel Integrated Graphics uses system shared memory for rendering resources. And the game need to correctly detect this and correctly calculate amount of video memory available for the resources. When we added this code, shadows appeared in the game, but it was running even slower. So World of Tanks team spent a lot of time to optimize shadow performance in the game. One of the major optimizations for shadows was separating shadow mapping algorithm used in the game for static and dynamic objects. For static objects like terrain or buildings, adaptive shadow mapping was used, where an array of shadow map tiles can be updated on demand. And for dynamic objects like tanks, where you need to update shadow map every frame, cascaded shadow maps were used. All those optimizations gave a good performance boost and also delivered a good quality. Our next task was to focus on the major bottlenecks and most complex frames. World of Tanks is an online multiplayer game, so it requires that gamers have good performance during the whole battle, even in the most complex moments. Dynamic resolution rendering is one of the techniques which led to improved performance in those moments by temporarily reducing quality by reducing the size of world rendered while keeping UI with the same resolution. Nowadays, many games use same technique on the consoles and on a PC, but in 2014, World of Tanks was one of the first games which implemented this technique. And it was working on every computer configuration supported by game, even for non-Intel configurations. But we also did some optimizations which are hardware specific. We developed a special path for vegetation rendering for previous generations of Intel computer graphics to ensure optimal performance for alpha-tested geometry with stencil. And of course, for such an enormous variety of computer configurations, it's important for the game to have very scalable quality settings. On this slide, you see 4 screenshots from the game running with a different quality at 1080p resolution and delivering performance from 166 FPS with the lowest quality to 13 FPS with an ultra quality. And every gamer can set his own combination of shadow, lighting settings, post-processing and special effects to have performance which he thinks is the best for him. And with all optimizations we did for more than a year period of time, we were able to improve performance by more than twice and have performance with more than 30 frames per second with shadows enabled. And thanks to dynamic resolution rendering, it was continuous through the whole battle. That allowed us to support way more gamers to have better performance, better visual quality, and a better gamer experience. With achieving those results, the team believed that we can accomplish even more ambitious goals. And it was time when the World of Tanks engine needed to be re-architected. And Bronislav will tell you this story. Bronislav, thank you.
Hi guys, my name is Bronislav and we continue our presentation with DX11 and Core Engine. By 2016, World of Tanks could run comfortably at 30 FPS on low-end and laptops PCs. However, it still used outdated DX9 API, and the next goal for us was to add support for DX11. Besides DX11, we needed to clean up our existing codebase, which had about 15 years of legacy code, we also wanted to prepare for the future graphics API and platforms. To solve those problems, we develop abstract render interface. Later, I will call it AREI. As the name suggests, it's basically a common rendering interface that can be used with various graphics API backends. Wargaming FX Framework is our in-house shader cross-compiler. It is similar to DirectX Effect Framework, but has much more functionality, especially in terms of concurrency. It allows us to specify in FX files shader techniques, render states, and shader permutation. AREI and WGFX allow it to submit render commands in parallel, and this is a huge advantage over the just DX9 and DirectX Effect Framework. The DirectX 11 support became a part of CoreEngine 1.0 together with our significant performance optimizations. In World of Tanks update 9.15, we released the first version of our internal proprietary core engine. It includes AREI and WGFX with two backends, DX9 and DX11. One of the main features that significantly improved performance by up to 30% was the usage of background render thread. The accumulation of render commands was done in the main thread, while the DirectX API calls, actual calls, were performed in background thread. One of the important graphical features at this time was the introduction of temporal anti-aliasing. After we added support of DX11, we had to catch up in terms of visual quality with the modern graphics level. Optimization was still the main or top priority for us. World of Tanks has huge audience worldwide, which is shifted towards old and slow hardware. Of course, we have players with good commodity hardware, but they are definitely not the majority. Therefore, when we had started working on the new graphics engine, we had a significant challenge. We definitely didn't want to lose the majority of our players with old hardware. However, we wanted to have modern, cutting-edge graphics in our game. One of the main paradigm of the new graphics engine was PBR approach, which included physically based shading model with photometric lighting units. New terrain system allows us to have huge 32 by 32 kilometer terrain, and terrain virtual texture and adaptive shadow maps are both algorithms that extensively cache the result of their work and provide a good balance between quality and performance. Improved water rendering featured volumetric waves and deformation particle effects, which allows us to have actual visual fidelity of the water deformation. New engine also included a pre-computed global illumination with Iridium's props grid, destructible objects with havoc destruction and interactive vegetation. Internal CoreEngine 5.0 became known for public as a just CoreEngine. CoreEngine was released as a part of the biggest ever World of Tanks update 1.0. To get full benefits of the new engine, all game art content had to be created from scratch. It's more than 1,000 models and objects on the space. Simple conversion to PBR wasn't enough because not only lighting model changed, but also content production pipeline. Geometric detail of all 3D models, including tanks, was very low, and because most of it were created in 2010, so we had to create it from scratch. Number of objects per map significantly increased also. Each reworked map had about 5 times more objects. The main achievement is that all of the existing graphics quality levels remain the same, and performance also stay on the same level. New graphics quality level, we added new graphics quality level called Ultra, and it was added specifically for the most powerful players' hardware. Here are some comparison shots to demonstrate graphics quality before and after introduction World of Tanks 1.0 update. As you can see, the difference is quite dramatic here. Although the visual changed substantially, gameplay-wise these maps remain the same. So actually gameplay wasn't changed. Now, after introduction of the DirectX 11 and better quality of graphics, now we were ready for the next ambition tasks. Make the engine ready for the new modern multi-core processor, as it was clearly visible from the players database that about 60+% of our players had 4+ core CPUs. And we really want to take significant advantage of using all of the available cores. And the first important problem to address and make the choice, choose the good task managers. Gladly, at the same time, Intel proposed to use its Intel Threading Building Blocks library. And when we together with Intel Corporation closely looked into the requirements, we decided that TBB specs and features was the obvious match for us. The API was easy to use, supported both functional and task-based parallelism, had robust and rich functionality, and the main point, great support from developer team from Intel company. It also supported on various platforms and fully open source, so it's open door for the moving to other platforms. This is how our engine works without concurrent rendering. You can see overloaded main thread, main render thread, and underloaded child threads. And as a result, GPU gets not enough work to be most effective. And on this diagram, you can see example how high-level frame render graph may look like. Having such high-level architecture of the frame is very helpful for everyone in the team to quickly understand what is the actual flow or order of execution and what subsystem depends on each other. Moreover, this code is really easy to modify, optimize, because all high-level information about coarse-grained tasks are located in one place. Task-based or functional concurrency works well here because what you need to do is just wrap up each task and add dependency, and that's all. As I previously mentioned, our engine uses TBB flow graph to gather command list for various subsystems in parallel and then flash them in a predefined order into the render thread. Unfortunately, if we do only one flash to the render thread per frame, it will make render thread stay idle because we have dependency between CPU and GPU. So we have to perform intermediate flashes to give the render thread some work as soon as possible at any given time. And now let's take a look at the average render frame on the Intel i5 CPU with 4 cores. This is the main commodity CPU at that time. Here we can see the main thread, here we can see the main thread which gather all of the commands into the number of independent command leads one by one. It takes a lot of time to do it, so it's about 17 milliseconds. And this is the render thread which is processing render frame. You may also notice that the render thread is idle for a pretty big amount of time. This is because our main thread can't generate render commands fast enough, so GPU stay idle. If we add 5 more tasks, TBB flow graph starts executing them concurrently on different threads with respect to dependencies. It's also interesting that in terms of TBB flow graph, there is no main thread anymore, and it acts like a usual worker thread. When we put all the render tasks into job system, overall frame rate is doubled. But there is some curious moment. This bubble is essentially show that we have to be careful with 2 things. The first, size of each individual render task, and the second, set of dependencies between this task and other. It might lead to such a big inefficiencies. So as you can see, functional or task parallelism or concurrency is pretty easy to implement. It requires us a minimal effort to write and support such code, and because we can take a high-level view of our render pipeline, we can easily make modification to increase parallelism in our engine. Unfortunately, high-level frame render graph requires us to reason about big chunks of work, which is not always optimal. Just because not all tasks have the same size or the execution time. Or not all tasks may be executed in parallel because some of them may have dependency on each other. So this approach quickly leads to the critical execution path. You may think about minimizing amount of dependencies between tasks, which is good, by the way, or subdividing task into smaller one, which may significantly reduce the readability of the code. Okay, but how could we improve performance while still keep our code base readable? Before we were using only functional or task parallelism, and there's also a data parallelism. So what we can do is to exploit data parallelism inside each subsystem independently, and be sure that TBB is going to do the rest. Thus, we still have easy to read and maintain high-level frame render graph, and each subsystem may produce additional tasks to be better utilize all available CPU cores. And now let's take a look at high-level CPU like i7 with 6 cores. Again, this is CPU, the most commodity at that time. We have ongoing render thread and set of render tasks executed in the main thread. The render frame takes about 12 milliseconds. And now the same frame, but with enabled concurrent rendering. As you can see, the render frame is reduced significantly, and moreover, all 6 cores are busy. But to reduce the critical path, big tasks should be subdivided into smaller ones. And by the way, this is a future work to do this subdivision even further. And we still have bubbles where CPU cores are idle, but the overall CPU utilization is much, much higher. To reduce the amount of bubbles, we are using data parallelism. And here you can see how VFX, our particle effects, prepare task, schedules additional subtasks to be executed in parallel on the other threads. So bubbles are eliminated, or at least number of them is significantly reduced. And now let's take a look how concurrent rendering improves efficiency and performance with multi-threaded rendering data preparation. This optimization allows to improve performance for about 50% for existing and new hardware configurations. And next, Dennis will continue our presentation with tank thread simulation. Thank you.
Hi, I'm Dennis, and I'm going to start my talk with an important part of a tank game, tank thread simulation. Currently, we have two major types of threads in the 1.0 release. On the minimal settings, we just render a skinned mesh of the tank thread and scroll the texture along it when the tank moves. Nothing special. Spline thread approach uses artist-defined control points to construct a spline and then places thread segments along it. Thus, we achieve the next level of geometric quality of the thread. Thread animation is also improved because we can vibrate the spline control points between wheels to simulate the change of the thread's tension. Spline tracks look very good compared to just skinned meshed, but unfortunately they have several flaws we want to address. The shape of a spline is hard to control. Because of that, when we vibrate its control points, some spline curves could penetrate the terrain and other obstacles. Spline also doesn't allow us to create hard edges to properly place the thread on blocky objects. We vibrate the spline control points using invisible springs, and the way the springs vibrate is quite unpredictable when you try to tune it. This results in a very difficult thread setup process for the artist. These problems motivated us to create a thread which would be physically simulated and produce better visual quality. We did several experiments with various physical models, considering quality and performance cost. And the final choice was to use the spring chain. Springs were less prone to jitter in our collision environment. Of course, they may stretch, which is not physically correct, but that stretch is gradual along the thread, thus visually not very noticeable. A nice bonus of the springs is that they naturally produce animations when a tank swings. This gives threads a much more natural look than we could achieve with the spline. The artist will also be free from tuning the thread animation because it's fully procedural. And last but not least, during the simulation, we could collide joints of the springs with the collision scene, producing much more detailed collision effects. So final solution is the following. The spring chain doesn't rotate around the tank. We snap it at 2 points at the front and back wheels, so it only swings with the tank and collides with the obstacles, producing the shape along which we scroll visible thread segments. The different parts of the track have different tension if the tank moves forward or backwards. To simulate this effect, we divide the thread in 4 parts and change length of springs for each part separately to control the tension along the whole thread. So at the collision phase, we do the following. We calculate a one-dimensional height field underneath each thread by doing several collisions tests with the environment. Then we test each spring joint against it. And collisions with the wheels are just a point against the disc. And the result is stable enough. Each thread is simulated as a job for TBB. To increase concurrency, we also exploit data parallelism by using parallel for and parallel reduce functionality. So due to heavy usage of multi-threading, tank thread simulation may even not affect the resulting performance. In 2018, we also worked on SIMD optimizations for tank threads. The modern CPU doesn't only mean multiple cores, but also new vector instruction sets. The first implementation of tank threads was using 128-bit SSE 4.2 vector instruction set to efficiently do vector math for spring simulation. But with the new 256-bit AVX2 set, it's theoretically possible to get a double performance. So our team started porting the code to the new instruction set. But as any new vector instruction set, there is a problem. Programmers need to know the intrinsics and know how to use them efficiently. It's also important to take care of data layouts and select the best possible one, array of structures or structures of arrays. And the first manual implementation we had only gave us 13% of performance improvement, which isn't small, but something that can further be improved. To solve those complex intrinsic programming challenge, Intel has a new tool. It's Intel SPDM compiler. It's a new open source LLVM-based compiler and C-style language made to generate highly performance vector code. Using SPDM, programmers can easily port their vector functions, writing it once and choosing the vector set which they want to use or which is supported on each gamer's PC. So with this compiler, supporting new vector instruction sets is becoming much more easy and efficient. So when our team tried the compiler, we got great results. Resulting performance was more than twice faster than original code and much faster than the first manual AVX2 implementation. But to get most optimizations, it's not just the compiler, but also the data layout also needs to be optimized. Next important feature I'm going to talk about is Havoc destruction. It is introduced as a part of World of Tanks 1.0 update. Our client physics collision destruction solution is based on Havoc third-party library. This physics engine serves as a physics simulation system and collision detection system. Havoc has a good tool set based on popular 3D editors such as Maya and 3ds Max. Also, it has out-of-the-box multi-threading support. To support good performance versus gameplay balance, our engine uses two different scenes inside Havoc library. The first one is the collision scene. It's used for accurate collision queries, and the destruction scene for destruction interaction. Collision scene uses compressed meshes of triangles, and they're almost identical to the actual model's geometry. It gives very accurate collision results, which is important while shooting, but it's too slow for the physics simulation. Destruction scene uses simplified convex decomposed models, which are very fast and lightweight for physical interaction, but they are inaccurate. This separation gave us much more freedom to our artists and lowered complexity of the content production. Havoc has its own task manager, which serves a number of internal Havoc threads. So this is the high-level look at our destruction system architecture based on the Havoc library. We have main thread, which invokes two threads. It's input-output system for loading and unloading physics assets, and main simulation thread, which generates and manages number of internal Havoc threads. Collision queries may be performed at any time and are completely thread safe. So this is what our engine threading system looked like before refactoring. We had a number of independent thread pools in different hours and a third-party subsystem. And these pools fought for the CPU time, which often led to inefficient task execution, which led to thread oversubscription. The problem was especially significant during some content destruction when lots of visual effects are spawned at the same time as physical parts interaction are being processed. So the solution was to move all task management to just one manager. The most heavy thread system except our main task system is Havoc, so we started from it. The goal was to use only Havoc interfaces without rebuilding library itself and not to break the process of library updates. We use simple single-threaded task queue from the Havoc side and mapped it to BB task graph. So the solution worked pretty well. This approach disabled double task handle management inside Havoc and TBB. Now let's take a look at core load before and after the update. On the left side, you can see the underloaded TBB threads while Havoc threads work. This led to FPS spikes and freezes on heavy destruction scenes. On the right side, all threads are loaded almost equally and performance spikes disappear. And now let's talk about our latest feature, ray traced shadows. After we made all the performance optimizations, we had budget to add new features. We made some experiments with GPU particles collision with tanks and realized that we could implement full real-time ray traced shadows. Since most of our players use DirectX 11, we decided to implement a version of ray tracing that doesn't rely on any specific hardware and that most of our players could enjoy. We are the first game to use real-time ray traced soft shadows in DirectX 11, and for BVH construction we use Intel Embry. Since we already used TBB in our engine, it was easy to integrate Intel Embry. So here are some comparison screenshots for our regular cascaded shadow map shadows and ray traced shadows. The three main advantages of ray traced shadows over traditional shadow maps are the following. So shadow maps miss lots of small details due to lack of resolution. Ray traced shadows produce correct contact shadows that are hard to achieve because of the depth bias in shadow maps. Ray traced shadows naturally generate proper physically based penumbra. So here are two comparison screenshots back and forth. And now let's talk about the implementation details of ray traced shadows. The general concept is similar to the existing hardware real-time ray tracing solutions. There are two levels of acceleration structures, bottom level and top level. Bottom level acceleration structure, BVH, is a level of 3D meshes. In our case, it is generated only once during startup for every part of the tank mesh and uploaded to the GPU. Hard-skinned vertices in meshes that are affected by one bone are treated as a separate static BVH instance. Bottom level acceleration structure, BVH, is a level of 3D meshes. In our case, it is generated only once during startup of every part of the tank mesh and uploaded to the GPU. Hard-skinned vertices in meshes that are affected by one bone are treated as a separate static BVH instance. In our game, tanks mainly consist of rigid bodies, so soft-skinned vertices are skipped. BVH refit is planned to be implemented in the future. Top-level acceleration structure is the level of mesh instances. We rebuild top-level BVH every frame using Intel Embry and upload to the GPU. Intel Embry uses multiple threads through Intel TBB. On the GPU side, in Pixel or Compute Shader, we do the following. We generate one ray per pixel that is jittered every frame in a uniform cone distribution. Then we perform BVH traversal and ray triangle intersections. Then we temporally accumulate the results, apply denoising passes, and the final step is our regular temporal anti-aliasing. Originally, we started with our own single-threaded BVH builder, which was extremely slow. Using Embry with TBB sped up per frame class BVH construction by more than 5 times. Memory-wise, there isn't that much data, up to 72 megabytes of bottom-level BVH nodes and triangles, and also up to 5 megabytes of top-level BVH nodes and bottom-level BVH instance metadata uploaded to the GPU every frame. So main optimizations that we made are the following. Major optimization was that ray trace shadows are cast only by tanks, and other objects use regular shadow maps. Tanks are our main objects in the game, and they're most detailed objects in the game, and they occupy a significant portion on the screen. We currently do not support alpha-tested geometry, which speeds up ray tracing because we don't need to store UV and lookup textures. We also use LODs for blast that corresponds to the correct LOD drawn on the screen, and this helps to avoid self-shadowing artifacts and improves performance since there are fewer triangles. We also just shoot 1 ray per pixel, which is enough with proper denoiser. If endotel is less or equal to 0, we skip ray tracing at all. However, it doesn't work for vegetation, which uses transmission. If pixel is already shadowed by traditional shadow map, we skip ray tracing as well. Additionally, we limited the ray trace distance to 300 meters. So speaking about performance, the highest quality RT shadows take 1.4 milliseconds on average on 280 Ti, which results in around 188 frames per second total, which we think is a very good result. We achieved good results on low-end machines as well. On Intel laptop with integrated GPU, lowest quality RT shadows take 5.6 milliseconds with around 54 FPS total. Even on highest RT settings on Intel laptop, total FPS is more than 30 FPS. In October last year, we released a World of Tanks Encore RT, which is a next version of a tech demo that we released before the big graphical update, World of Tanks 1.0. And the main feature of an Encore RT is real-time ray trace shadows. So it's a tech demo that basically has a launcher where a user can set up desired graphics quality and launch a pre-recorded real-time replay of a tank battle in the desert map. Performance score is displayed after the end of the replay. There are 3 levels of quality for ray trace shadows. The lowest level corresponds to just basic hard shadows. Medium level is soft shadows without denoising, and highest level is soft shadows with denoiser and temporal anti-aliasing. And full release of the ray traced shadows in the game is planned later this year. And that was all. Thank you for your attention.